In today's video, we're going to talk about the mathematics of circular motion and this idea of being weightless. So after watching this video, you should be able to use and apply some of the equations that will be presented in this video, and then get a better understanding of what it actually means to be weightless. So let's get right into kind of talking about equations. And the first equation I'd like to discuss is orbital speed. Orbital speed. We've been working with this equation that's called Newton's second law. And basically Newton's second law is F equals ma. And that force is the net force. I should really write that in there. So F net equals mass times acceleration. So that's nothing new. We also know that the acceleration of an object undergoing circular motion is acceleration equals v squared over r, right? So basically what I'm going to do is I'm going to drive an equation to figure out the orbital velocity of an object. And so what I'm saying here is if I want, I could actually replace this a here, this acceleration, right there in that formula. So I could really say F net equals mass times v squared over r. That would be totally okay to do, okay? So that's another way of writing F net. Now, in a previous video lesson, we talked about this law called the universal law of gravity, which was created by Newton. And that law basically said that the force of gravity acting upon an object is big G times m1 times m2 all over r squared, or the distance between them squared. Okay, now here's something to think about. What is the only force acting upon an object, or maybe I should say a projectile? And whether that projectile is a satellite, a moon, whatever, what is the only force acting upon that thing? Well, the only force acting upon it is the force of gravity. And so the net force is the force of gravity in most of the things that we're talking about when we're talking about like circular motion of satellites, say the moon, a satellite, a spaceship that's orbiting the Earth, whatever the case may be. And so something we could do here is we could actually say the net force acting upon an object that's undergoing circular motion around like a planet or whatever is the force of gravity, right? That is the only force acting upon it. So something I could actually write is I could set these two equations, this equation equal to this equation. And if I did that, I would have m times v squared over r, which is that guy right there, equal to big G times m1 times m2 all over r squared, okay? And using your noggin, I think we know that we can cancel some of this stuff. And I should really probably have said, this is the mass of the satellite, or whatever, the moon, or whatever it is that's orbiting the object. And m1 would also be the mass of the satellite. So some things I could cancel here would be like, I could get rid of this m. I could get rid of this r and just call this r instead of r squared. And all of a sudden, you're left with this. If I were to like kind of simplify this, I would have, and I'm going to write it over here on the left side of the screen so I have space. V squared equals big G times the mass of the central object that's orbiting, whether it's the Earth or the Sun or whatever the case may be, divided by r. Okay? Or what I could do, and you say, man, just tell me what the dang thing is. This will be it. To get rid of this square piece, I could say v equals the square root of big G times m central divided by r. That is it. Okay, so here's an equation for you that might be useful when we talk about circular motion or satellite motion, where the velocity of this object undergoing circular motion around, say, the Earth or the Sun or whatever the case may be, is equal to big G, which is just a constant, times the mass of the object that it's orbiting divided by its radius. Okay, and that equation I think will come in handy every now and then. And if you don't get all this stuff like how I derived this, that's fine. Maybe take a look at it later on as you go through some of the problems, and it might make more sense later. Okay, let's continue on. The equation for acceleration then, basically, for a satellite that is, and whether the satellite's the moon, a man-made satellite, a spaceship, whatever the case may be, can be expressed in terms of masses and radius. So the acceleration equals big G times the mass of the central object divided by the radius squared. Okay, so far we have two equations, an equation for velocity and an equation for acceleration. Okay. The third equation I'd like to present to you is dealing with Kepler's third law. And if you remember in the previous video lesson, I talked about Kepler's third law, that it was this law of harmonies. It's kind of this relationship between orbital period and the radius of a planet and all that good stuff. So here's the actual mathematical formula for Kepler's third law. So basically, what does all this stuff mean? Well, t squared, t is the period of the satellite. And I'll write that in here. T equals the period of the satellite. Okay, so how long it takes to orbit the object. And typically, this is going to be represented in seconds. Okay, so a lot of times you'll get the answer and you'll convert it into hours or days or years or whatever you need. Okay, so typically it's going to be in seconds. Cubed is the distance or the radius from the object that's orbiting the Earth or the Sun or whatever it might be to the center of that object. So let's just, for instance, say here's the Earth, and here's the object that's orbiting around the Earth, okay? I'm looking for the distance from this satellite to the center of the Earth. That is R. And typically, you're going to need this in meters, is what you're going to be looking for. So you'll be converting that into meters for the most part. Okay, in just a second, I'm going to do an example problem dealing with Kepler's third law, so we'll be able to see it in action. Okay. Just a side note, though, before I go into that example, an important concept kind of arises as you look at the three equations that I just presented to you. In all three of those equations, for the period, the speed, and the acceleration of an orbiting satellite, none of them cared about the mass of the satellite itself, which is kind of interesting to think about. So whether you're a little pebble orbiting the Earth, or if you're just a big old spaceship orbiting the Earth, the mass of that object does not matter. The only mass that matters is what is the mass of the object that's orbiting around. So whether it's the mass of the Earth or the mass of the Sun, that's what we care about. I could care less about the mass of the spaceship or the mass of the pebble or the mass of the moon. It doesn't matter. It actually doesn't care. And that's similar to basically projectiles launched on Earth. The mass of a projectile has no effect upon the acceleration towards Earth and the speed at any instant. If you remember way back when, I talked about dropping an elephant and a mouse from a plane, and both would actually accelerate downwards towards the Earth at the same rate, 9.8 meters per second squared. And it doesn't matter that the elephant is 1,000 times heavier or more massive, I should say, than the mouse. It doesn't matter. They all both accelerate at the same rate towards the Earth. Okay, so kind of interesting, at least I think. So let's do a practice problem here. This might get to be pretty large. Let me move some of this stuff up because this asks for a lot of things. And I might almost need to do another slide here. So it says a satellite wishes to orbit the Earth at a height of 100 kilometers or 60 miles above the Earth's surface. Determine the speed, acceleration, and orbital period of the satellite. And they give us some information up there. Basically, they tell us that the mass of the Earth is this, and I would not expect you to memorize that. I would always give you that. And the radius of the Earth is that, and I would not expect you to memorize that as something I would give you. Okay, so let's do the first thing here. Let's figure out the speed, or also known as the velocity. Okay, what is the velocity of this satellite? Well, I had given you an equation right from the get-go on this video that V equals the square root of big G times m central, or the mass of the central object, over r. And big G, if you guys remember, is 6.67 times 10 to the negative 11th. And I'm going to keep units out for right now just because it's going to get so messy. But that's a 6.67 times 10 to the negative 11th. The mass of the central object is the mass of the Earth. So the mass of the Earth is 5.98 times 10 to the 24th kilograms. So 5.98 times 10 to the 24th. And again, I'm going to leave units out just because it just saves space. Divided by the radius of, or the distance from the satellite to the center of the Earth. Now notice the radius of the Earth is 6.37 times 10 to the 6 meters, and this satellite is not right on the surface of the Earth. Instead, it's 100 kilometers away from the Earth. And so we're actually going to need to change kilometers into meters. If you remember from the previous slide, I said we're going to need to make basically that r distance be in meters. So 100 kilometers is actually 100,000 meters. Okay, so I just would add that to the radius of the Earth. And if you do that addition problem, 100,000 plus 6.37 times 10 to the 6, you get a radius of 6.47 times 10 to the 6th meters. Okay, and this is all square rooted. Don't forget that. A lot of people do forget that. And so if you do this math problem and you do the work, you should get a velocity of about 7.85 times 10 to the 3rd meters per second. Okay? So pretty fast, right? But that makes sense. It's got to be going pretty fast to be able to not like basically crash into the Earth. Okay, so that would be the velocity. Okay, now that I know the velocity, I can find the acceleration. And if you remember, the acceleration of a circular or an object undergoing circular motion is a equals v squared over r. Okay, well I know v squared, it's 7.85 times 10 to the 3rd meters per second, which I'm going to leave the units out again, squared, over the r, which we know is right there, 6.47 times 10 to the 6. 6.47 times 10 to the 6th. And if you do this math problem, you get an acceleration of 9.53 meters per second squared. 9.53 meters per second squared, which is interesting because notice, what does the acceleration do to gravity if you stand on Earth? The acceleration due to gravity if you stand on Earth is 9.8 meters per second squared. This number is smaller. How come it's smaller? Well, it makes sense. The satellite is not right on the surface of the Earth. It should be a little bit smaller because it's in outer space. It's still under the influence of Earth's gravity, but it's not quite as strongly under the influence of Earth's gravity because it's orbiting the Earth. It's above the Earth's surface. Okay, the last piece is to determine the orbital period of the satellite. All right, the orbital period of the satellite. And I think I might make a blank page here and do it on this. So if you need to go back to see the data, be my guest. But this is using Kepler's third law. So Kepler's third law basically says you have t squared over r cubed equals 4 pi squared over g times m central, or the central body in which this is orbiting around. Now we're interested in finding out what t squared is. So basically what I'm going to do is I'm going to multiply both sides by r cubed, and you're going to have, or I'm sorry, take the inverse of r cubed over here, and so you're going to have basically multiply by r cubed over here, and so this one cancels, and then you're left with just t squared. Now I'm going to do a little bit of the algebra on my own, so hopefully again if you're struggling with that piece, feel free to ask me questions about it, but basically you're left with t equals the square root, because that's, I'm going to get rid of that square piece, 4 times pi squared times the r cubed, so 6.47 times 10 to the 6th cubed, all over 6.67 this gets to be a lot of numbers. Sorry, 6.67 times 10 to the negative 11th multiplied by 5.98 times 10 to the 24th, which is the mass of the Earth. And don't let the numbers all intimidate you. I mean, basically, this is just throwing stuff in a calculator, and as long as you punch the numbers in correctly, you would get the correct period, which is going to be the amount of time it takes for this satellite to orbit around the Earth. And that amount of time is 5,176 seconds. Or if you're looking for it in hours, it'd be about 1.44 hours to orbit the Earth. Okay, and that would be my answer. All right, so that's an example of using Kepler's third law to solve a problem that we basically went through and got the velocity, the acceleration, and then used Kepler's third law to finish that baby off. That takes care of this video. I'll see you guys next time.